Now we have a graded index fiber. This is another kind of fibers which is completely different from the step index fiber. Okay, for step index fiber, we have N1 throughout the core and we have N2 throughout the cladding. Okay, and it is changing from N2 to N1 in a step fashion or staircase fashion, right? Now for graded index fiber, what we do, we will gradually change the index from N2 to N1. Okay, we will gradually change. That means for step index fiber, it will change in a step. Suddenly it will change, but for graded index fiber, it will change gradually. Okay, and the refractive index variation can be written in this way: N1 into 1 minus 2 delta R by A whole to the power alpha square root for R less than A, that means inside the core, and it is N2 for R is greater than A. Okay, that means inside the core it will vary in this way. So depending on the value of alpha, we have different profile. Okay, for alpha equal to 2, this one, for alpha equal to 2, we have parabolic profile. Okay, for alpha equal to 1, we have a triangular profile. So depending on the value of alpha, we have different profile. Okay, now what is the utility of such fibers? Let us see what we can do with this type of fiber. Actually what happens, since the fiber core refractive index uh, change uh, gradually, we can assume that it will behave just like a, it is a kind of focusing arrangement. Okay, it's a kind of focusing arrangement. So this ray will be reflected within the core itself. For step index fiber, the reflection takes place at the core cladding interface, because here we have the refractive index variation. But for graded index fiber, we have refractive index variation throughout the core. So wave will be reflected within the core itself, and all these rays will be reflected and will appear again at the same point. That means it will be as if we have a uh, convex lens present right here, and all these rays are actually focused right here. Okay, so basically what happens for step index fiber, if we have any kind of disturbance or any bending type of thing, they will try to produce different modes. But here, because of this focusing arrangement, the number of modes will be restricted. Okay, so that is the utility of graded index fiber. Let us see how exactly the thing is changed for graded index fiber. So basically we can assume that the index is changing in this way. So if we divide this whole core region into n number of uh, layers, so for this layer we have refractive index of n1, for this layer we have refractive index of n2, for this layer we have refractive index of n3, and so on. Now the wave will travel and they will gradually bend at each layer. Okay, at each layer, so the bending will be gradual. Now at certain point it will be totally reflected. Okay, and then it will again gradually bend, right? So inside the core, it is not that it is moving in the straight path, it is gradually bending, right? Because the refractive index is changing. Okay, and the total internal reflection takes place within the core itself. It doesn't need to go to uh, the interface between the core and cladding. Okay, so because of this focusing arrangement, uh, that the number of modes will be restricted. Okay. Now, what will happen for the skew rays? So similar situation exists for skew rays. Follow the longer helical paths. So these travel for the most part in the lower index region at greater speed. So giving the same mechanism of mode transmit time equalization. Hence, multimode gradient index fibers with parabolic or near parabolic index profiles cores have profile cores have transmission bandwidths which may be order of magnitude greater than multimode step index fiber bandwidths. Consequently, although they are not capable of the bandwidths attainable with single mode fibers, such multimode gradient index fibers have the advantage of large core diameter, maybe greater than 30 micrometer, coupled with bandwidth suitable for long distance communication. So this is the advantage of gradient index fibers. Let us have a numerical problem. A gradient index fiber has a core with a parabolic refractive index profile which has a diameter of 50 micrometer. The fiber has a numerical aperture of 0.2. Estimate the total number of guided modes propagating in the fiber which when it is operating at a wavelength of 1 micrometer. So V number equal to 2 pi by lambda a into numerical aperture. So all the values are given. So it becomes 31.4, and number of modes may be of the order of v square by 4. Under this condition, it is v square by 4. So it is nearly 247. So fiber supports 247 number of guided modes. Okay, so um, lesser the modes supported by the fiber, greater will be the speed or bit rate.